Section 16.7 is where we stop prior to spring break. So in this video, I'm going to go over all the examples in this section. The main topic of this section, of course, is finding hydronium concentrations of weak acid solutions. And if we examine this problem in general, it's richer than equilibrium problems in general because we actually have to concern ourselves with two simultaneous reactions. Hydronium is generated both by the ionization of the acid itself as well as the autoionization of the water. Now, the amount of hydronium generated from the water, for the examples we'll look at, is going to be so negligible compared to that from the acid that we can effectively ignore the autoionization of water. However, we should be curious as to when we have to consider both of these. And when we have to consider both, is when the acid solution is dilute in its formulation. That is to say, when the acid concentration, what we can consider the initial acid concentration or the formulated concentration, is sufficiently small such that the amount of hydronium generated from the acid is comparable to that from the water. And we have to consider both of these reactions simultaneously. Let's also make the distinction between finding hydronium concentrations in weak acids versus strong acids. Now, in the case of a strong acid, the acid will completely dissociate. So whatever the initial concentration is going to be equal to the hydronium concentration when the reaction completes itself. So for example, if one were to formulate a 0.1 molar hydrochloric acid solution, that is to say, put 1.1 moles of hydrogen chloride in 1 liter of water, the hydrogen chloride would immediately dissociate such that you would have a 0.1 molar solution of hydronium ions. However, again, if the formulated concentration is sufficiently dilute, the amount of hydronium generated from this strong acid will be comparable to that of the water, such that one has to consider both of these reactions simultaneously. Finding the equilibrium concentrations of hydronium follows the equilibrium problem that we've examined in general, where we essentially solve for the hydronium concentration at equilibrium based on the equilibrium constant formulation. And effectively, given the initial concentrations of our acid, we will set up a ICE table and thus formulate our equilibrium variables in terms of an unknown variable, the so-called change variable X. And this book is very good at providing recipes to common problems. And this 6-step recipe is something that we will try to adhere to. So the first example in this section, example 16.5, asks us to find the hydronium concentration of a 0.100 molar hydrocyanic acid solution. We're given the initial concentration of our weak acid, which is 0.1 molar, and we want to find the hydronium generated. So again, with all these problems, the chemistry is never really stated. So the first thing we want to do is write the reaction here. So we have hydrocyanic acid. So we form this. In this particular case, we want to think of taking 0.1 moles of hydrogen cyanide and dissolving it in 1 liter of water. And what is going to happen? Well, this dissolves and then it reacts with water and proceeds to equilibrium, generating hydronium and the conjugate base, cyanide. Okay, so what do we know? Well, let's make a table, the so-called ICE table. So we're given the initial concentration of our hydrocyanic acid. We seek the equilibrium concentration of our hydronium. And we are also going going to have to consider the, this is the problem working with the Sharpie, you can't erase. Okay, so this is the cyanide. And so let's be clear here, the initial, the change, and the equilibrium. So this is our ice table. Okay, so the initial 0.100 molar. We're going to neglect the autoionization of water, but initially, of course, in water, there is some hydronium, but effectively it's so small that we can neglect it. And initially, the hydrocyanic acid has not ionized. Now, we expect a change, and thus we will generate X moles per liter and X moles per liter of both hydronium and our conjugate base. So at equilibrium, 0.10 minus X, X, and X. And again, what we are ultimately going to solve for are the equilibrium values. Okay, just to cyanide. And this is at equilibrium, and HCN at equilibrium. So the value of Ka is tabulated, and again, from, what was it, table 16.5, I believe, we can find these values. But let's, and specifically, what is the value? The value is, of Ka is 4.9 times 10 to the minus 10 to the minus 10, so it's small. Our equilibrium concentration of hydronium is X, cyanide is X, and of our acid is 0.100 minus X. And let's see here, I'm going to treat this as a virtual whiteboard here. So we have 4.9 times 10 to the minus 10 equals X squared over 0.100 minus X. Given the order of magnitude of this, if we completely neglected X, then X squared is going to be on the order of 10 to the minus 11. And so that gives us a value of X that's on the order of 10 to the minus 5 to 10 to the minus 6, which is quite small. So the X is small approximation is expected. And so now what we're solving for is this equation, namely 4.9 times 10 to the minus 10 equals X squared over 0.100. And working through this, this is just equal to X squared equals 4.9 times 10 to the minus 10 times 0.10 is 4.9 times 10 to the minus 11. And thus X equals the square root of 4.9 times 10 to the minus 11. And there's ways that we can estimate this, but we can just punch it into the calculator, and voila, we get 7.0 times 10 to the minus 6. So is X small enough? And to answer that, really what we're going to examine is this ratio, X over the initial HCN. And this is actually and we're going to look at this as and we're going to express it as a percent. Really what this is, and if this is less than 5%, we feel justified in the X is small approximation. And what this percentage is the percent autoionization of our weak acid. So in this particular case, this evaluates to 7.0 times 10 to the minus 6 divided by 0.100 times 100%. And that is 7.0 times 10 to the minus 3%. okay, which is, yes, way less than 5%. So X is small, it's justified. And in the end of the day, our hydronium concentration is 7.0 times 10 to the minus 6 molar. So that's what we were asked to find. Look at that. Such as these problems of using Sharpies here. As a formal check, we would plug these values back in and examine that the equilibrium constant that we get from 7.0 and 7.0 times 10 to the minus 6 molar for the cyanide, and our equilibrium concentration, that these are in fact consistent. In fact, they are. So I'm going to skip that step because I've run out of paper. Notice here in the book, the last step, step 6, which I did not do owing to lack of space on the paper, but basically, once you've solved for your equilibrium concentration, go back and plug in all your equilibrium values back into the equilibrium quotient formulation, and solve for your equilibrium constant again, and make sure it checks with the one that you were given or looked up. The 4 practice problems, again, these are worth doing if you like extra practice. And of course, the solutions to all of these 4 practice problems are found at the end of the book. So example 16.6, here we're asked to find the pH of a 0.200 molar nitrous acid solution. Okay, so example 16.6, so we're given this initial concentration. Find the pH at equilibrium. Well, we're going to get the pH from solving the equilibrium problem. So again, what's the chemistry? Always write out the chemical reaction. Make sure we understand the chemistry. Equilibrium problem. So that's the chemistry, and the Ka for this is 4.6 times 10 to the minus 4. All right, so what do? Well, we make up an ice table. So let's do an ice table. With time, you can just probably just cut to the chase. Let's see here, but you do enough of these, what you find, at least for weak acids, that in the end of the day, your ice table looks the same, and you can pretty much just jump to the fact that, hey, I'm going to be solving the same type of quadratic equation again and again and again, and it's just a question of whether or not I'm justified in the X is small approximation. So initial change in equilibrium. So what do we have here for the initial value? Okay, 0.20. Okay, again, neglect the autoionization of water, and of course this is 0, and X moles of this will ionize per liter, generating X moles per liter of hydronium and X moles per liter of our conjugate base, 0.200 minus X, and X and X. And so when I talk about, many of these problems, you're going to find that you're just basically going to be able to cut to the chase. Again, Ka, the equilibrium constant reads the same. I mean, we often can talk about the generic weak acid equilibrium problem, but it always reads like this: the equilibrium. So the product of the hydronium concentration and the conjugate base divided by the weak acid concentration at equilibrium. And specifically, we have this expression to solve: 4.6 times 10 to the minus 4 equals x squared over 0.200 minus x. And here we're going to invoke the x is small approximation, but we'll find that we can just barely get away with it. This is sufficiently large such that the autoionization constant is actually going to be close to 5%, but less than 5%. So x is small. All right, so now, coming over here, what are we solving? So we're solving for this problem here. 4.6 times 10 to the minus 4 equals x squared over 0.200. And if I go ahead and rearrange this, I'm going to be solving for square root of 4.6 times 10 to the minus 4 times 0.200. And this evaluates to 9.6 times 10 to the minus 3. So is x small enough? And the answer is yes, although very barely. So again, we're looking at the percent autoionization. So really, again, what is this? This is the equilibrium value of the hydronium divided by the initial value of our weak acid times 100% to make it proper percent, which in this case equals 9.6 times, oh, it's right there, 0.200 times 100%. This equals 4.8%, which is just less than 5%. So yes, but just barely. Okay, so what's the equilibrium concentration? Hydronium, it's 9.6 times 10 to the minus 3 molar. So the pH is just minus the log of 9.6 times 10 to the minus 3. And that is going to equal to 2 decimal places, 2.02. And that right there is what we were asked to find. Now, as a check, we didn't do this in the last problem, but just to be thorough, we're asked to reconstruct our value of Ka based on our equilibrium values. So again, 9.6 times 10 to the minus 3 squared divided by 0.200 minus 9.6 times 10 to the minus 3. Okay, so this is and let's see here. So you notice it's slightly off, but that accounts for the x is small approximation. Yeah, close enough. And notice I did calculate in this example the equilibrium constant again, but rather than using the initial acid concentration, I actually use the equilibrium value. Hence, my value does not equal the one given to me, but the value basically shows the error in the X is small approximation breaking down when it gets close to 5% regarding the auto-ionization of water. Example 16.7, we look at the case when the X is small approximation does not work. Here we're asked to find the pH of a 0.100 molar chlorous acid solution. And what we'll see is that on the first approximation, or the original approximation with the X is small approximation, the percent ionization is going to be sufficiently larger than 5%, such that we'll either have to solve it exactly using the quadratic formula, and that is how the book does it, or we can use the method of successive approximations, which I will demonstrate in the solution. So we have chlorous acid reacts with H2O, generate hydronium, and chlorite. So that's our chemistry. And again, recall that equilibrium concentration of hydronium, right? Equilibrium concentration of CO2. And this value equals, from the table, it's actually relatively large. It's 0.011. So if we set up an ice table, I'm just going to skip that, but we'll think about what an ice table will generate. For every X moles of chlorous acid that ionizes, we generate X moles of hydronium and X moles of chloride. So the system we're going to be solving for in terms of the X variable is going to be this one, 0.100 minus X. So 0.100 minus X is our equilibrium concentration of chlorous acid. Now, we're going to invoke the X is small approximation here, but we'll see that we really can't get away with it because this is so large. So nonetheless, we'll solve this system. X squared over 0.100 equals that. And rearranging and just cutting to the chase, this is equal to our equilibrium constant times the initial concentration. This evaluates to 0.033. And of course, this will show us that X is not small enough. Why is that? Well, is X small enough? Well, what is the percent ionization? The percent ionization is X divided by our initial concentration, which is 100 times 100%, which is equal to 0.033 divided by 0.100 times 100%, which is equal to 33%, okay, which is greater than 5%. So clearly the X is small approximation does not work. So what do we have to do? Successive approximations. So we'll now introduce X0. This is our initial guess under the X is small approximation. And now we're going to go back to this setup and we're going to solve for the next approximation. We're going to call that X1. So what we'll do is we'll just write out this setup, but now I'm going to write 0, 1, 1 equals X1 squared. So X1 is our next approximation, and that's equal to 0.10 minus X naught, which is this value. if I go ahead and I solve for this, I'm going to get an equation that x1 equals the square root So working through that, what do I find? I find that this evaluates to 0.027. Okay. In general, we have an equation for generating the next approximation from the previous, and that's what this is, 0.011, the equilibrium constant, times our previous approximation of the equilibrium concentration of the acid, Xn. And so now if I make up a little table, I'm just summarizing calculations that I've already done. So this is n and this is xn, so n equals 0, 1, so our original successive 3, and geez, this table, might have to put it, I might have to do it another time. All right, so let's just go through this. So 0.033 was our first guess, the original, and then the next approximation, 0.27. If I take this, plug it in there for x2, I get 0.028. And then if I then go in and plug it in again, what do I get? I wind up on for the third successive approximation, I get the same value. So that's the method of successive approximations. Of course, you can always solve this by the quadratic formula. It's your choice. So, okay, so let's just successive approximations or solve quadratic. That would be another option. But the advantage of this, you've already put in the initial investment work-wise. So you may as well, continue with it and improve upon it. So what are they asking us to solve here? So again, given the initial, find the pH. Okay, so what do we know? Well, we know that, let's see here. I'm be careful how I write this. So the hydronium concentration is therefore 0.028 molar. And from this, we can calculate the pH. And now I'm going to do the check. And the check on this, again, is to calculate the value of our equilibrium constant. And so what do these evaluate to? So now we're actually going to use the values that we actually got through successive approximations. And again, here I'm going to use the actual equilibrium concentration. And that evaluates to 0.011, which is, of course, what we started with. So that all checks out. So notice in the book, we have on the exosmol approximation, we have a percent ionization of 33%, greater than the 5%. And the book chooses to solve it exactly using the quadratic formula. And they get the value that we got. In other words, our value through successive approximations converges to the exact value within the same number of sig figs. And notice in this case, when they do check the work, they put in the, exact equilibrium values. Example 16.8 is sort of a twist to the previous examples, because here we're given the formulation of a weak acid, and we're given its pH, and then we're asked to find the ionization constant. Okay, so example 16.8, they give us this initial concentration, and they give us the pH. They want us to find the K. So what are we really talking about here? So what we have, a generic acid, HA. This is our acid. It's going to react with water, hydronium, conjugate base. And so Ka, which is what we want to find, is equal to HA at equilibrium. Now, by giving us the pH, they effectively give us this. So let's go ahead and work that out. pH is equal to minus the log of, so our hydronium concentration is equal to 10 to the minus pH. And in particular, this is 10 to the minus 4.25, and that evaluates to 5.6. Okay, 2 decimal places, 2 sig figs, 10 to the minus 5 molar. So we have that. What then is our concentration of HA? Well, that would be the initial, which is 0.100 minus the change. So for every X moles of HA that ionizes, we generate X moles of hydronium. Well, we know what those X moles of hydronium are, 5.6 times 10 to the minus 5 molar. So that's molar. Okay, this is to 3 sig figs. That's going to wind up equaling that. And then lastly, what then is our, this is also our conjugate base. So when it's all said and done, Ka is equal to 5.6 times 10 to the minus 5 times 5.6 times 10 to the minus 5 over 0.100. And this evaluates to 3.1 times 10 to the minus 8. The percent ionization of a weak acid is something that we have been discussing in all of these example problems. And again, it's defined here for us. A question we might want to consider is how percent ionization depends on the initial concentration of the acid. So in example 16.9, we'll revisit the nitrous acid solution that we examined previously, but now we'll look at a solution that has a higher concentration, 2.5 molar as opposed to the 0.2 molar that we looked at previously, and we'll compare the percent ionizations. So example 16.9, we're given some initial concentration of, hey, nitrous acid. Hey, where have we seen that before? So again, let's recall the chemistry of this. Some nitrite in solution. So where have we seen this problem? So let's go back through the example. So no, it wasn't 16.5. Oh, there it is. Okay, so in example 16.6, we looked at this. Now, what was different there? We were given a 0.2 molar solution. Here we have one that's approximately 10 times or more concentrated than that. Now, going through the ice table and setting this all up, in this thing, we had to find the pH, but eventually we did have to solve for the percent ionization. We found that it was 4.8%, which is just barely less than 5%. And the fact that we were able to get away with it is that this is sufficiently concentrated such that the X is small approximation is going to work. So let's consider just working. We're not going to even go work out the ice table. We'll just write 4.6 because that is the equilibrium constant. And again, Ka is just the equilibrium values. So we'll go ahead and we'll just write this out. In this particular case, it's going to equal x squared 2.5 minus x. Now, proceeding with this problem, we'll go ahead and invoke the x is small. And thus we're going to wind up with 4.6 times 10 to the minus 4 equals x squared over 2.5. So x equals 4.6 times 10 to the minus 4, our equilibrium constant, times the initial concentration. And we're going to go ahead and solve for that, and it comes out to being 0.034 molar. So that's the hydronium concentration. And what then is the percent ionization? So again, that's this equilibrium value, the equilibrium divided by HNO2 initial, and specifically this is equal to 0.034 divided by 2.5 times 100%, which is 1.4%. All right, so that's what we're asked to solve for. How does that compare to the previous problem when we had a more dilute solution? It was 4.8%. So we see a generality here, percent ionization of an acid versus concentration. Specifically versus initial concentration. So consider a generic acid. This develops hydronium. Now, the Ka for this is just the and percent ionization is, of course, defined as the amount of hydronium generated with respect to the initial concentration of our acid times 100%. Things we know. At equilibrium, these two are equal. And the equilibrium value of HA is just going to be equal to the initial concentration minus and this is, as we said, the using the X is small approximation, which is consistent when the percent ionization is very, very small. The equilibrium concentration of our weak acid is going to be very, very close to our initial concentration, provided the amount of hydronium generated is small. That is to say, if the percent ionization is small. So this is approximately this. And so if we now put these values in here, so I'm now going to do this. And what we can say is Ka is approximately equal to H3O plus H3O plus over HA initial. And if I divide both sides by H, the initial concentration of our acid, what do we get? Well, we get and so, in other words, percent ionization when it's small, so in the limit that percent ionization goes to 0, we have established this expression for it, namely, so percent ionization is going to be equal to the square root of Ka over the initial acid concentration times 100%. In other words, this becomes approximate. So the more concentrated our acid formulation is, the smaller the percent ionization. And so the reason why the X is small approximation, we can get away with it, is that the ratio of the ionization constant and the initial weak acid concentration is significantly less than 0, such that this evaluates to less than 5%. So percent ionization as a function of concentration might appear a little bit counterintuitive. The more concentrated you are, the smaller the percent ionization, although the more hydronium you are going to generate, the higher the concentration. Mixtures of acids, it pertains to the last example in this section. So let's consider two cases. What happens when we have a strong acid and a weak acid in one solution? if the concentrations of these two, the initial concentrations, are comparable, clearly the strong acid is going to generate more hydronium than the weak acid, which is only going to partially ionize. So in cases such as these, where again concentrations are comparable, we go with the stronger acid as generating the most. In the case of a strong acid, one that completely ionizes versus a weak acid that doesn't completely ionize, we can simply focus on the ionization of the strong acid alone to calculate the hydronium concentration. In the case of two weak acids, a similar argument applies if the ionization constants of the two differ by orders of magnitude and the concentrations are comparable. Essentially, we go with the stronger acid as generating the bulk of the hydronium, and we consider that generated by the weaker acid as to be completely negligible. Here in example 1610, we have a mixture of two weak acids, and notice the concentrations are comparable. Okay, so example 1610, we're given the initial concentration of our hydrofluoric acid and that of our, I believe our what do you, I don't know the acid. All right, well, find the pH. Okay, so let's just talk about the chemistry here at play. So we have this equilibrium reaction occurring. We also have another equilibrium reaction occurring. And I'm writing the autoionization of water here because this is something that we've been neglecting all along, but we have been justified in doing so. So three equilibrium reactions occurring simultaneously. All three of them generate hydronium, which, however, is going to generate the most. And if we were to look at these three reactions independently, what we would find is that the concentration generated by the first, owing to the fact that the equilibrium constant is the largest between these two, and they have concentrations, initial concentrations at least, that are comparable, we would find that this generates an overwhelming amount of hydronium, more so than this, like orders of magnitude more. So in effect, what we're going to focus on here is this first reaction, and we just consider this first one alone. Now, if we wanted to go about this properly, what we could actually do is consider all three reactions simultaneously, introducing a change variable, x, for this problem, another change variable, y, for this problem, and another change variable, z, for this problem, where x, y, and z represent the amount of hydronium generated by these three reactions. And then for each of these, we would actually find the equilibrium concentrations of fluoride, hypochlorite, and hydroxide based on the combined equilibrium value of hydronium and the initial concentrations. This is doable. It's three equations, three unknowns. We can solve for all three. But ultimately, what we would find is the hydronium concentration to leading order. And within the number of significant figures that we have, is going to be equivalent to just solving this. So the rest of this problem is just another weak acid problem. And so for that, let's go ahead and solve for it. So Ka is equal to the hydronium concentration generated by hydrofluoric acid times the fluoride concentration over the equilibrium. And so this is 3.5 times 10 to the minus 4. And if x moles, so we're going to have our old standard, and the initial was 0.15 molar, 0 minus x. So that's the system we're solving. And we will go ahead and make the x is small approximation. And rearranging this, we find that x is equal to the square root of 3.5 times minus 4 times the concentration. And this winds up giving us 7.2 times 10 to the minus 3. And the percent ionization is less than 5%. 7.2 times 10 to the minus 3 divided by 1. Ooh, well, just barely, 4.8%, just barely. Okay, but still, we're gonna go with it. So and therefore the pH is equal to okay, so that's what we're asked to solve. Now, for comparison purposes, although I've already stated it, so that's the, so again, this is the hydronium concentration generated from this first reaction occurring independently. We can ask, we've already stated so much, but we can actually explicitly show that if we were to solve for this, the hydronium concentrated generated from this reaction occurring independently, it would be substantially smaller than this. So let's go ahead and just show that. And so now, working with the second, our Ka is equal to, again, the hydronium concentration, hypochlorite divided by the initial concentration, the equilibrium concentration, using the x is small approximation, 2.9 times 10 to the minus 8. We're going to have x squared over, the initial is 0.1, 0.100 minus x. So now, proceeding, x is small. We wind up solving for x squared is going to be equal to 2.9 times 10 to the minus 9, which is equal to 29 times 10 to the minus 10. Why do I do that? Well, because I'm doing this in my head. And so this x, therefore, is equal to the square root of 29 times 10 to the minus 5, and that's the square root of 29. Doing this in real time, ladies and gentlemen. Wow, it's exciting. Let's turn on my calculator here. What's the square root of 29? I should be able to do that in my head. I mean, 4 times 4 is 16, 5 times 5 is 25, so it's a little greater than 5, somewhere between 5 and 6. All right, specifically, I'm going to say it's going to be like 5.5, but all right, square root. Where's the square root function on this? Darn it. So, all right, hate this calculator. Second square root 29. Yeah, 5.3. It's 5.4 times 10 to the minus 5. In other words, the hydronium concentration generated from that would be 5.4 5. So again, going back, what do we see? This one generates an equilibrium concentration of 7.2 times 10 to the minus 3 molar. This one is going to generate a hydronium concentration, again, occurring independently in a separate vessel. So imagine these three reactions occurring separately. 5.4 times 10 to the minus 5. And of course, this one occurring independently, 10 to the minus 7. If you were to add all three of these together, what you would find, to the number of significant figures we have, this plus this plus this would actually just give you that, because 10 to the minus 3 is 2 orders of magnitude larger than 10 to the minus 5, which is 2 orders of magnitude larger than 10 to the minus 7. That's just doing it independently. And what you would also find is that if you actually do all of these, if you solve for all of these three simultaneously, the algebraic equation that you would generate to the first approximation would reduce to the one that gave us this. And that's all I'll say.